We're going to do another example now. In the interest of testing your own understanding, I might suggest that before you watch this video, you go ahead and see how much of this you can get done before you watch the solution. Okay, so our task here is let's find the electric field at a point P above one end, so last time we were above the center, and it was vertical, of a long positively charged rod with a uniform charge density. This uniform charge density, this is telling us that our charge density lambda is equal to Q over L, and it's the same throughout the rod. No more charges kind of bunched up in one area than another. So let's go through our whole process, and we'll make some notes as we go. Let's go through the steps, even though we're not going to write all the steps out. So we're going to identify one little bit of charge dq. We're not going to pick it at either end or dead at the center. So here's our little bit of charge dq. We want to draw the electric field made by this dq. It's a positive charge, so the electric field points away. This is a little bit of charge, so it makes a little bit of field. We call that little bit of field dE. It is a vector, so we draw it with a vector symbol. It has components. The x component is horizontal, dEx, and our y component is vertical, dEy. We know that dE equals k times dq over r squared. R is from our point to our charge. So there's our R. We know that to get our x and y components, we're going to have to use some trig. I'm going to call this angle theta. So dEx equals dE times cos theta, and dEy equals dE times sine theta. Okay, what else we got? Let's identify our parameters. So from the origin to where our charge is, that's a distance along the x-axis, so that's going to be a value x. That one's going to be variable. So if we picked our dq at a different spot, it would have a different x. So this x is a variable, and our y is the vertical distance between our rod and our point P. That one's going to be constant. So there's our y, that's constant. Cos and sine. Cosine theta is adjacent over hypotenuse, x over r. Sine theta is opposite over hypotenuse, y over r. Okay, so we've got lots of information down here now, and these are certainly the sort of details you should be putting in when you're solving this sort of problem. We want to find our x and y components of the element, dEx and dEy. After we write down those elements, we're going to add them all up. Before we get started, we might ask, is either of these final components going to sum to 0? Do we get cancellation here? Maybe I'll let you think about it for a minute and then we'll revisit. Oh, we didn't write down what r was. So r is the hypotenuse of a right angle triangle, so r is going to be x squared plus y squared to the 1/2. Okay, I think we've got all of our information down there now. What about our dq? Oh yes, let's write down our dq. We say we want to write it in terms of the parameters. So dq has a length, it's a horizontal rod, so it has a length that's a little bit in the horizontal direction. It's a little bit dx. So the amount of charge on this element is going to be the charge density lambda times its length, which is a little bit in the x direction dx. Okay, now I think we've got it all. So for our components, let's start with the y. dEy equals dE times sine theta. dE is k times dq over r squared. Sine theta is y over r. dq is lambda times dx times y over r cubed. So I've got k times lambda. I'm going to swap my y and my dx. My r cubed here, remember r is x squared plus y squared to the 1/2. Then when I take that to the cubed, it's going to give me to the 3/2, just like it did the last time. I'm just not going to write out that extra step this time. Notice this is our y component. It's got a dx here. This is absolutely correct. This dx comes from the geometry. It's because that little bit of length is in the horizontal direction. Okay, there's dEy. Let's also do dEx. That's dE times cos theta. equals k times dq over r squared times x over r. K times lambda times dx times x over r cubed. K times lambda times x times dx. R cubed is x squared plus y squared to the 1/2 all cubed, or x squared plus y squared to the 3 over 2. So there's our dEy and our dEx. To find our total electric field, we're going to have to sum each of these bits up. So Ey is going to be the sum of dEy, and Ex is going to be the sum of all the dEx's. So now let's come back to, are any of these going to be 0? Do we have any symmetry working in our favor here? So let's think about the direction of all the dEy's due to every bit of the rod. So no matter where we take the dq, our dE is always going to point left and up, right? So if dq is here, dE is like this. If it's here, it's like this. If it's here, it's like this. So my dEy's always point up, and my dEx's always point left. So I'm going to say for this problem, no cancellation at all. We don't have any of that symmetry here to make things cancel. Okay, let's get cooking on finding our Ey. Maybe I do need a fresh piece of paper here. So my Ey equals the integral of dEy, which is the integral of k times lambda times y times dx over x squared plus y squared to the 3 over 2. I can take my constants out front. Y is a constant, so k and lambda and y come out front. Integrate dx over x squared plus y squared to the 3 over 2. I need my limits of integration. I'm going to go from one end of the rod to the other. So here's one end of the rod. There's my x initial. That's located at x equals 0. And there's my final end of the rod. There's my xf. That's at the total length of the rod. That's my xf equals L. So from xi equals 0 to xf equals L. Again, you can look this up in a book if you don't feel like integrating it out. We get k times lambda times y times 1 over y squared times x over square root x squared plus y squared. That looks right. Evaluated at L and 0. Okay, so we've got to put in x equals L and x equals 0. Gives us, and then one of these cancels with one of these, k times lambda over y, L over square root of L squared plus y squared minus 0 over square root 0 squared plus y squared. This whole bit is just 0. K times lambda times L over y square root L squared plus y squared. We totally want to be thinking about the sign. All of our dEy's point up. It means that overall our net electric field points up. So this is positive, and we know it's going to be positive, so we're happy with the sign there. Let's do our Ex next. Remember, all of our dEx is pointed left, so overall our Ex will point left. Ex is the integral of dEx equals the integral k lambda x dx over x squared plus y squared to the 3 over 2 equals k times lambda. X is a variable that can't come out front. X dx, x squared plus y squared, 3 over 2. And look this up in a book if you wish. Integrating over the same limits, x equals 0 to x equals L. We get k times lambda over minus 1 over the square root of x squared plus y squared equals k times lambda minus 1 over the square root L squared plus y squared minus 1 over square root 0 plus y squared. So that's just going to be a plus. That's going to be 1 over y down here. Ex is k times lambda minus 1 over the square root L squared plus y squared plus 1 over y. When we look at our Ex, this whole term, so This bit is going to be smaller than this bit, so this whole term ends up being positive. We know that our EX has to point left, so we've got to be careful with that when we write our answer. EX points left, so we know that we want that to be negative. EY points right, points up. We know we want that to be positive. And we know that from our picture here because we thought about which way it had to point. So now let's incorporate this as we write our answer. Our total electric field is the X component, K lambda, minus 1 over square root L squared plus Y squared, plus 1 over Y. The direction has to be in the negative X direction. And then we have to add in the Y component, which is already positive. And that gets a J hat for the Y component. So there's the electric field above one end of a positively charged rod.